In the last video, we introduced the concept of log as the growth rate needed for 1 unit to become x units in 1 unit time. But simply giving it a name doesn't tell you how to calculate it. Let's use log 2 as an example to see how to compute it. It means 1 unit becomes 2 units, so a net increase of 1 unit. But this extra unit doesn't come from the mother cell completely, because if you remember, its offsprings are constantly growing too. So the extra growth from the mother cell should be smaller than 1. Now, how to calculate it? Let's consider the incremental growth by looking at equal growth size each step. For example, let's consider the next little period where the cell grows by 10%. Let's assume this 10% comes from the mother cell completely. So here we write down the contribution from the mother cell. It's an approximation, but since the interval is small, the error is small too. Then viewing this as a whole, going into the next period, where again it grows by 10%. Now, of this 10% growth, how much comes from the mother cell? 1 over 1.1, right? Again, viewing this as a whole, 1.2 unit. Going to the next little while where another 10% growth happens, now the mother cell contributes 1 over 1.2. You can see a pattern here. Going to the next little while, it contributes 1 over 1.3, 1.4, so on, until 1 over 1.9, because we consider 10 growth steps and we start with 1 over 1. So to calculate log 2, we can approximate it by summing them up. It's about 0.718771. Now let's make it more precise by considering 100 growth steps. So each step we consider 1% increase and see how much comes from the mother cell. So we have the whole 1%. For the next growth, 1 over 1.01 of it, 1 over 1.02 of it, 1 over 1.03 of it, all the way to 1 over 1.99 because we consider 100 steps. Now summing them up, we get a more accurate answer, 0.695653. Now, how to verify if it is correct? In the first section, we talked about how E can be used to express change. So knowing a specific rate of change, the final outcome can be calculated as e to the power of r. Now we are saying if you don't know the rate, but you know the end result, then doing log operation on the result can give us the rate. So that means if we use log 2 as the growth rate on top of e, we should get a result of 2. Does it? Now we can plug in the number for e and log 2. Using the calculator, we get roughly 2. It's not exactly 2, because both e and log 2 are approximations. But if you make them more and more precise, it will be closer and closer to 2. The log 2 we manually calculated is pretty similar to what you get using the calculator. For a more general case where the end result is x, here is how to calculate the rate log x. It changes by x minus 1, so you break down the total change into n steps, let's call it delta u. Then log x can be computed by this series, where you add up the weighted average contribution from the original unit. It might not be the best algorithm to calculate log, but it gives you some rough ideas. Then you can check if it's right by using it on top of e, and verify that it indeed gives you the same end result.